let's look at determinant of elementary and upper triangular matrices. So I introduced three types of elementary matrices. These are um, matrices which are corresponding to three elementary row operations. Yeah? And then upper triangular matrix is one where all entries below the principal diagonal are zero. So let U be an upper triangular or a low triangular n by n matrix. Then I want to show a determinant is the product of diagonal entries of U. Yeah. So I have an upper triangular matrix. Let's look at this matrix: A, B, C, D, E, F. Okay. So these entries are zero. These entries are zero, and I have upper triangular matrix. So I look at the entries on the principal diagonal. Yeah. Then what it says is that determinant is the product of the diagonal entries. Okay. So we will let us prove this, uh, but let us also state the results about elementary matrices. So consider the elementary matrix Tijm. That is, we are multiplying ith row by m and adding to the jth row. Okay, when I is not equal to j, then determinant of this matrix is 1. Remember how this matrix looks like. Okay, so let us say T12 of 5. Okay, T12 of 5. So we're adding the first row to the second row after multiplying by 5, and we'll do this for identity matrix. So this is the identity matrix, and we perform the row operation, that is adding 5 times the first row to the second row, and so this will be 1 0 0 5 1 0 0 0 1. So this is my T12 of 5. Okay, so look at Tij of m. So add, this is the elementary matrix where we have the ji entry as m, and other entries are like in identity matrix, and I is not equal to j. Then determinant of such a matrix is 1. Now take the elementary matrix which is obtained by interchanging ith and jth row of identity matrix, then its determinant is -1. This is clear from alternating property. Yeah? Alternating property gives this. Okay. Then look at the row operation where we multiply ith row by a number m, then its determinant is m. So this matrix is upper triangular, ith row multiplied by m, other entries are all 1. So this is an upper triangular matrix, and so if we prove determinant of upper triangular matrix is product of diagonal entries, then this will follow. Okay. So basic fact is about the upper triangular matrix is that determinant of upper triangular matrix is product of the entries on this principal diagonal. Okay. Now we want to we will show by induction on n that determinant of A is, look at the nth row, expand by the nth row. Okay. If you take this n by n upper triangular matrix, I want to expand by the nth row. So I proved determinant function, existence of determinant function by using the first row. In the same way, I can use the last row of a matrix. Then when I use the last row, then according to the signs, I will have -1 to the power n plus 1 times un1 determinant of un1. Then this will be determinant of un2. Finally, this is determinant of unn. Okay, but if you have upper triangular matrix, in the last row, all these are 0 except for unn. Okay, so only this term survives. Other terms are 0. Okay, so we just get determinant of u equal to this. But unn, what is unn? Unn is obtained by deleting the last row and the last column. If you delete from upper triangular matrix the last row and last column, again you get an upper triangular matrix. So apply the same formula for this. So u and n came out, when I apply determinant of u and n, there will be a sign, and u n minus 1, n minus 1 will come out. That is the entry on n minus 1, n minus 1 entry of u. So now these signs have to be taken care, and I leave it for you to think about this, that the signs will all multiply to 1. Okay. So determinant of a upper triangular matrix is product of the diagonal entries. Okay. Product of diagonal entries. Or we can apply the same principle to lower triangular matrices. Then we will expand by the first row. We want to prove the same result for low triangular matrices, that determinant of a low triangular matrix is product of diagonal entries. You expand by the first row and use induction, and you will come out with the same fact that the product of a determinant of a low triangular matrix is product of diagonals. Okay. Now these facts, they follow from this first fact, because these elementary matrices are either upper triangular or lower triangular. Okay. All elementary matrices are either upper triangular or lower triangular. So the three facts about elementary matrices follow. Okay. So if the third operation changes determinant to m, that is, if I multiply ith row by m, then I have a upper triangular, I have a diagonal matrix whose entries are 1, 1, 1, and the ii entry is m, and therefore determinant of this upper triangular matrix is simply the product of diagonal entries, which is m. In the third part, determinant of a matrix which is obtained from identity matrix by interchanging ith row and jth row, that by alternating property is determinant is minus 1. And the second part follows by the fact that it is an upper triangular or low triangular matrix. So its determinant is product, and the entries on the elementary matrix E are all 1 on the principal diagonal. So its determinant is 1. Okay. So we know the determinant of elementary matrices. Yeah, we know the determinant of upper triangular matrix, and then we can find determinant of any matrix using the either any row or any column. Okay. So let us. So that gives us enough techniques to calculate determinant of a given matrix. But many times a matrix is written as a product of two matrices, and let us prove that determinant of product is product of determinants. Now, if you use a formula to prove this, you can say, okay, let us prove this by 2 by 2. So determinant of a 2 by 2 matrix, I know it has 4 terms. I mean, it has one term, right? Determinant of x, y, z, u is xu minus yz. Okay. So I know determinant as a formula, but it has n factorial terms. If it is n by n matrix, determinant of a n by n matrix has n factorial terms. So if you just plug in into the formula, it becomes a very complicated thing, but it will check. Ultimately, it will check. Now, I want to give you a conceptual proof. Okay, without computing the determinant, we can show determinant of product is product of determinants. Yeah, we will simply show that the two sides are determinant functions on n by n matrices. So A and B are n by n matrices. AB is an n by n matrix, and determinant is a function on n by n matrices. The left-hand side is a function on n by n matrices, but we are looking at product. Right-hand side is product of two determinant functions. We will show that they are one and the same. Okay. So we want to show that determinant of product of two matrices is product of determinants. Okay. Yeah. So we know this fact from multiplication of matrices, that if I want to multiply two matrices A and B, then ith column of A times B is obtained by multiplying A with the ith column of B. Yeah. This fact I proved earlier, that ith column of A times B is A multiplied with the ith column of B. Okay. So we will show, therefore we prove that the AB is nothing but this matrix whose column vectors are AB1, AB2, ABN. Okay. And we want to show that this determinant function is determinant of A times determinant of B. Okay. Now here comes the non-trivial step in the proof. So look at this. Look at this. Okay. Keep A fixed. Keep A fixed. Define a new function on the space of n by n matrices f b1, b2, bn. B is now a varying n by n matrix. A is fixed, and I define this function f as determinant of ab1, ab2, abn. What is this? This is just ab. Okay, so I'm keeping A fixed, and I'm defining a function on the space of n by n matrices. F of B is equal to determinant of A times B. Okay, I will show that F is multilinear alternating. Okay, so function is alternating. Why? Because suppose two column vectors of B are equal, then two column vectors of this matrix AB are also equal. Bi equal to Bj, Bi equal to Bj, then this has two equal column vectors, and therefore this is 0. So F is alternating because determinant is alternating. Okay. Yeah. Now I will prove the multilinear property. Now multilinear property. Shanmukh, can you stop this?
Yes, sir. I'm just seeing who is on. They muted, I guess. Mudhav Shanmukh. Sir, yes, I've muted him.
Yeah. Okay. So suppose C is a n by 1 column vector and take any scalar A, and I am proving multilinear property. So kth column is bk plus ac. I could have taken a bk plus alpha bk plus beta c, but the proof is the same. So here is my matrix. In the matrix B, I am replacing kth column by bk plus ac. So that is by the definition of F is the determinant of AB1, A times bk plus ac, ABN. Okay. Now A times bk plus ac by properties of matrix multiplication, it is this matrix, this column vector. Okay. I apply multilinear property of determinant function. Now this is determinant function, so I can separate A bk and A times ac, and I get determinant of AB1, ABK, ABN, and determinant of AB1, AAC, ABN. This A comes out again by multilinear property, and therefore this is equal to FB1, B2, Bn plus A times FB1, CBn. So F is multilinear. So F is multilinear, so any multilinear function, we have proved that it is a scalar multiple of determinant function, where the scalar is the value of the function on identity matrix. So F on B1, B2, Bn must be determinant of B1, B2, Bn, and F of E1 up to En. But what is F of E1 up to En? F of E1 up to En is determinant of AE1, AEN by our definition of F. But AE1 is A1, the first column vector. AEN is the last column vector. This is determinant of A. So value of F on identity matrix is determinant of A, and therefore this becomes determinant of A. This is determinant of B, and therefore this is the determinant of AB. Yeah. So I didn't apply any formula for determinant of matrix. I simply constructed a function which is multilinear alternating and used that this multilinear alternating function is a scalar multiple of the determinant function. And then I used the formula for F to find out its value on identity matrix that turned out to be determinant of A, and that gives me determinant of A times B is determinant of A times determinant of B. So this is the beauty of the axiomatic method, that complicated proofs become simpler if you follow axiomatic approach, because we have proved that determinant function is unique. Any function which is multilinear, alternating, and normalized is uniquely determined. So to prove some formula for determinant, I will simply use this fact that the given formula has three properties, and therefore it must be determinant of the given matrix. Okay, so that's the idea behind getting these simpler proofs. Yeah. Last slide, determinant and invertibility. So let us quickly check that we can use determinants to test invertibility. This is not a practical criterion. Yeah? Invertibility of a matrix is checked by using Gauss-Jordan method, that find the row canonical form. If the row canonical form of a n by n matrix is not the identity matrix, the matrix is not invertible. If it is invertible, then the row canonical form must be identity matrix. Okay. So let us see that determinant can also be used to check invertibility if you have access to the formula. Okay. Yeah. So Vecha person is worried about proofs. Okay. So let me tell you, proofs will not be asked in exam. Exams will be always problem oriented. But in order to be good at solving problems, you must understand the proofs. Yeah, you must understand the proofs. That's what I expect, that you look at the class notes and read the same material from the textbooks and be clear that you understand the proofs. Okay. So this proposition says that if A is invertible, determinant is not zero, then determinant of A inverse is 1 over determinant. And if determinant is not zero, then A is invertible. So we are saying that a matrix is invertible if and only if its determinant is not zero. And if it is invertible, determinant of A times determinant of A inverse is 1. So they are reciprocals of each other. Okay. If AB is I, then A is invertible and B is equal to A inverse. We have proved this before, but here is another proof using determinants. Okay. So let's look at part 1. It says that if A is invertible, then determinant is not zero. So if A is invertible, then I have A times A inverse is identity. Determinant of product of two matrices is product of determinants. So it says determinant of A inverse times determinant of A is 1. And therefore, determinant of A and determinant of A inverse, they are reciprocals of each other. Yeah. Now, part 2, we assume that determinant is not zero. We want to prove A is invertible. So suppose A is not invertible. Yeah. If A is not invertible, then there is a non-trivial solution to AX equal to 0. In characterizing invertible matrices, I proved this equivalent formulation of invertibility, that AX equal to 0 has only trivial solution if and only if A is invertible. So if A is not invertible, there is a non-zero column vector, so that AX equal to 0 and this is equal to 0. And that says that now one of the xi's is not 0 because this is a non-trivial solution of AX equal to 0. And so I can suppose x2 is not equal to 0. I can use this equation to write down a formula for A2 as a linear combination of other column vectors. So some column vector of A is a linear combination of other column vectors of A, and therefore when I write the determinant by multilinearity and alternating properties, we will see determinant is 0. If one column vector is a linear combination of other column vectors, just use alternating multilinear property to see that determinant is 0. Part 3, if AB is I, then A is invertible and B is A inverse. So if AB is I, take determinants. So determinant of A times determinant of B is 1. So determinant of A is not equal to 0. Determinant of B is not equal to 0. So A is invertible by part 2. And so B is equal to A inverse A times B. And that is A inverse AB. AB is identity. So this is A inverse. So B has to be A inverse. Yeah. Okay. So now we have two proofs that whenever AB is identity, just this one equation rather than B A equal to identity. If we just have one equation, then it implies that A is invertible and B is the inverse. And invertible matrices are exactly those whose determinants are not equal to 0. Okay.